Okay, so let's make a start. So this week we are continuing on the first day of today, finishing off function objects and looking at Lambda functions. So this is a continuation from the end of last week. And then the second part of today, we're going to be looking at exception handling and dynamic memory management. And that will take us through today, Thursday, and possibly the start of next week. So on Thursday, we looked at this problem. We had a vector, and we're asked to write a program or a function to find any value in this vector that's in the range 5 to 10. And we said, how would you solve this if this was an exam question? And pretty easy. The answer to this, if this was a first year exam question, would be go write a method that looks a bit like this, build check range, takes them a vector, goes through each element of a vector in a for loop, and returns true or returns false if there's a value within the range 5 to 10. But we said, it's not very generic. What happens if we want to check values in the range 10 to 15? At least in this answer to this problem, we'd have to change the whole function. And we could add in some parameters, but this isn't necessarily the most effective approach, okay? And so the question that we asked is, can we use STL algorithms to help us out? And the STL algorithm that we looked at was standard find if, which is included in hash include algorithm. And we looked at the idea of function objects. Can someone give me the 2-sentence version of what a function object is? What is a function object and how does it differ from a normal object or differ from a function? Yeah?
It's a class object that overloads the call operator.
Yeah, that's basically it. It's a class object that overloads the call operator. And what does this mean that we can do? What can we do with function objects? Yeah, just keep going.
Use the function call syntax you used to with the parentheses.
Yeah, so you can treat the object if it was a function. And because the call because the call operator is overloaded, it works. Okay? And so here is the function object that we're looking at on Thursday. That has a constructor that takes in the lower bound and upper bound. Has the overloaded call operator, which also takes in the value that we're looking at, and returns true or false if that value is within that lower bound and upper bound range. And so we can construct that function as a temporary object at that point inside this find if. Okay? And we said they're more function objects are more powerful than pointers or functions because they can contain state, e.g. in this case they contain the range. Okay, so function objects are very powerful. Okay, so that's whereabouts we're up to. What we're now going to look at is what's called bind objects. And there's a function in the standard library called bind. And it's a general purpose function adapter. What this means is it can take any callable object, e.g. a function or function pointer or another functor, and it can generate a new function object that adapts the parameter list of the original object. What this means, I have function f here, takes an int a, b, c, okay? I can wrap this function f inside a function object by calling standard bind, pass it in f. The standard placeholders thing here means this function object is still going to take in some parameters. And so copy whatever we pass into this bind object that we generate. The first parameter, the second parameter, and then 100. Okay, so this auto G1, this automatic generated bind function object, wraps void f. Remember, void f has got a, b, c as things being passed in. We want a new function object, G1, that's going to take in two things, position 1, position 2. The third thing it's going to have is 100. That 100 is going to get copied into int C. This means on line 10, G1, we can call G1 with value 1, 2. That's going to print 1, 2, 100. The reason for that is that 1 and that 2 is going to be passed straight through to F for a function object. This 100 that was set up over here is going to be passed in over here. Okay? So this bind generates us automatically a new function object. On line 11 down here, we've got a second call to bind to create a G2. This has the placeholders swapped around. Okay, so 2 and 1 swapped around. Still has 100 at the end of it. So when we call G2, 1, 2 like that, now it prints out 2, 1 because it's swapped this 2 and this 1 around here. So the second parameter gets passed into A, and the first parameter gets passed into B. And so the bind operator, or the bind function, can wrap and do interesting things with existing function objects, functions, function pointers. Now, why might you do this? Okay. Oh, sorry. First of all, here's an example of how we might do it with our range object. Okay, so here's a different version of our range class. Okay, it's got the call operator overloaded, passing in 3 things. So this version of the class range isn't actually maintaining state. We can wrap that functor with bind, passing in 5, 10, and the standard placeholders for whatever's going to be at this vector here. Okay, and it works as the same as before. Okay, if you're confused about some of these slides, go back and take a look at Thursdays because we're picking up right from where we stopped on Thursday, okay? So, if you already know C++, previous to C++11, there was a thing called bind first and bind second, okay? Standard bind is just a generalization of bind first and bind second, okay? And you don't need to worry about understanding it, but you need to worry about the general idea behind bind. Okay? So what bind is doing. So here's some more examples. Okay? Here's my vector again. Okay, I want to count if the standard greater than int, count if things are greater than 10. The standard greater int, okay, is basically a functor that kind of already exists in C++. I'm doing a bit of hand waving here, okay? It's a function object adapter. We're going to talk about that on the next couple of slides, okay? But it's something that already exists that we can bind first or bind around, okay? And so what we want is we want a functor or function object generator for us that says if something's greater than some value. Okay, so in this case, we're creating a bind object whereabouts if a thing's going to be greater than 10, it's passed into it. Okay, and so count if v.begin, v.end, create me a temporary bind object if it's greater than a certain value, and pass the second parameter in as being whatever that iterator is currently pointing to. Okay. Now again, don't worry necessarily about understanding too much about how the stuff works. Okay. There is lots and lots and lots of code samples. Okay, for how these things work. I have bind.cpp. I don't actually know what's in it. Okay, so bind.cpp is the one that we were looking at on the slide before. I don't think I have this one. Actually, I might do. It might be called oldbind by chance. There you go. Oldbind.cpp. There it is. Oldbind.cpp. Okay, it's the same code as what you're seeing there. Okay, and it's not going to print out anything because no printouts. Yep. Question.
Why vulnerable to the pointer invalidation?
Why isn't this vulnerable to point? What do you mean by pointer invalidation?
So the iterator invalidated, because you're passing in.
Oh, you could still pass in an invalid iterator and everything would explode.
Oh, so this is.
Of course it is. So you're passing in v.begin, v.end, okay? If you did not pass in something that made sense, if you passed in, if you had another vector called q, if you passed in q.begin and the second parameter being v.end, it may or may not work. You've got to be sensible about how these things work. Okay? So yes, of course this can have invalid iterators passed into it, like most code. Okay? Basically that's just don't be silly when you code. Okay? And later on today we might talk about exception handling and how you might deal with some of this stuff. Okay? But my point being is there's a whole lot of code here and code samples, particularly for week 4 ones. Okay, you should go take a look at. Okay, so there's bind.cpp, there's old bind.cpp, and on the next couple of slides, if we get to it, no, in a few slides' time, we're going to look at another big example of bind. So the standard template library has a lot of function objects already available. Okay, they're inside the header file functional. Okay, and so they provide these function objects that we can use for negation, addition, equal to, not equal to, greater than, less than, logical or, logical not, etc. Okay? And where you can use the standard bind algorithms to modify these function objects for how we want to use them. Okay? Again, for textbook and other things, we'll go into a lot more detail about this. And so the reason for having these function objects and these standard function objects and these bind functions and these adapters is so that we can increase the flexibility of function objects. Okay? Because they're functions that convert one function object into another function object. Okay? So we have arguments like not 1 and not 2. Okay? And say if we have a function called, or a function object called isOdd, okay, which returns true if something's odd and false if something's not odd, okay? We can wrap that in a function object adapter called not1. Okay, this is probably going to need a standard in front of it, but standard not1. And so it's just going to, as you can imagine, reverse the output of this. Okay? So say we had the method or function object is odd, we didn't have is even for some reason. We can simply go standard not1 is odd, and reverse it and then create is even. Okay? And we can do things like that. Okay? So bind objects are very, very powerful. But having shown you all that, I'm not going to focus too much about bind objects for the rest of the semester. The rest of the semester, we're going to be primarily looking at Lambda functions. Anyone know Lambda functions already? Anyone? A couple of people hand waving? Okay. If I stuff this up, you can tell me. Okay? Lambda functions are far more powerful than bind objects. Okay? Lambda functions allow us to, inline, create many little functions. They get compiled into function objects, okay, but we don't have to care about how those function objects work. And so we can write little helper functions when we need to without the overhead of a whole ton of declarations and definitions, or even thinking about the syntax of how this thing all works. And so here's the same problem that we've been dealing with for the last 2 days. How do I find in this vector if values are between the range of 5 to 10? And I've shown you a function, I've shown you a function pointer, I've shown you a function object, I've shown you how we might do it with the bind object. Okay? Here's the solution in one line of code. In the middle of this algorithm call, a standard find if, I actually declare in line this piece of syntax here that at first you're going to think looks really quite weird. Square brackets, normal brackets, squiggly braces. That's the syntax for a Lambda function. Okay? And so when this syntax gets seen, the compiler generates an unnamed function object that looks something similar to that. It expands that all out into a function object. Okay? But you don't have to care about that. All you need to care about is the syntax of the Lambda function. Okay? And the next couple of slides will go through what you can do with Lambda functions and why they're so powerful. Okay? So a Lambda function looks like this. It's got what's called a capture list, a parameter list, a return type it goes towards the end of there, and then the main function body. So this is quite different to probably how you've seen functions declared before. Okay? The capture list is a list of local variables, okay? So from the outer scope, a list of local variables that can be available in the enclosing function. Okay? So with our function objects that we've seen before, we couldn't really include local variables into there unless we pass them in as parameters or pass them in as constructors into those function objects. Here we can just say these are the things that we want available within this named function. We still have a standard parameter list. Okay, parameter list, which is these are the things that we're passing in like a normal set of parameters. And we still have a return type, but both the parameter list and the return type can be left out. Most of the time the return type is left out. Most of the time, not always. And we can store a Lambda function into a named type. Okay? So I can say auto f equals square brackets like that, don't capture anything, okay, but those square brackets are required, return 10. Here's the Lambda function, it just simply returns 10. I haven't created a function called int return 10, open close brackets, open close braces, return 10. Nope, I've just done it. Auto f equals square braces, return 10. And also notice the scoping. The scoping does not need to sit outside the scope of other functions. Okay, this is just an inline function basically. And so I can go standard cout f, and I still call it like a normal function. Okay, standard end L, prints out 10. Okay, and this covers off the idea of closure. Okay. Now, I'm not going to explain closure. I'll probably do a really terrible job if I attempted to. But if you're into some more theoretical computer science type stuff or different programming languages, closure is quite an important concept. Okay, and you can go take a look at it. So I'm going to go through some examples over the next few slides about what we can do with Lambda functions. And so here's an example, okay, about how we might pass some arguments through to a Lambda function. Okay? And this one is available at lambdaarguments.cpp. Okay? And so what you're seeing here is you're seeing two different ways of being able to sort a vector of words by size. The traditional way in which you might have done this, okay, the traditional way in which you might have done this, you might have written a function called isShorter and said, pass in string 1, pass in string 2, return size 1, string 1.size less than string 2.size. You might have done that. And you might have called this function called standard stable sort, words.begin, words.end, passed through reference to a function. You might have done that as a function object. Okay? Now, at this point, this isShorter is in the global namespace. Okay? So this isShorter we can call from lots of different places. Maybe you want that, maybe you don't. Okay? But for the whole reason why we've created this isShorter function is simply because we want a way of being able to define a sorting order over this vector. Okay? We can do that with a Lambda function. Well, in this case it's in 2 lines, but it's the same idea. Rather than this call out on line 18 to isShorter and isShorter being all defined up here, In line, we can, again, go square braces. Pass in the arguments, the same as what we would have done up in is shorter, but we've just done that in line. And then this return body just goes in there. Okay, so, and this will get compiled out at compile time and work. Okay? And so this is a lot cleaner, depending on what you're doing. This is a lot cleaner because you can, at this point, understand exactly what the stable sort is doing. The stable sort is sorting by size defined here. Okay, I don't need to go and look up the definition for is shorter. Okay, these lambda functions allow us to define our own ability to sort things or compare things in many different ways. Okay. And so I could keep on saying that they're very, very powerful. When we look at multi-threading up in week 9, we can write an entire piece of multi-thread code in a Lambda function and just create a new thread on it, just like that. Okay? So let's take a look at Lambda captures. Lambda captures are the things that go inside the square bracing at the start of a Lambda function. And so here I have what's called capture by value. Int v1 equals 10. Auto f, okay, so I'm going to store this function, is equal to square brackets v1, return v1. So I've created a function that takes in v1 and just returns its function, returns its value. Okay, it's not the most exciting function in the world. Okay. But then I say v1 is equal to 0, okay? And now if I say auto j is equal to f, okay, so get me the return from f, okay, so j is going to be an int. But the value of j is going to be 10, not 0. Okay, because the value is captured and copied when it's created up there. Okay, so that's different from how a normal function declaration might work. When you create for Lambda capture, it gets copied. Okay? If you capture by reference, which you can still do, okay, j will still be 0, because you capture by reference, so it stores for reference to a thing, okay? But you must make sure if a reference still exists when that function is called. If a reference doesn't exist, you're going to be in for a world of pain. So lambdas should be defined, declared, written out as close to when you're going to use them as possible. Okay? Don't just arbitrarily define all your lambda functions up at the top of your code and then try to use them like normal functions. They work different to normal functions. Okay? They're designed for sort of inline little short snippets of code. It makes sense to define things. If you've got a very, very long, complex set of code, still go for a normal function. Okay, so this is the big example I'm going to show you, which is aptly named biggies. Okay, where's it got to? That one. Okay, I can't actually find my. I can't actually find my Lambda function version of this in my code. Okay, but this code is called biggies, and it's doing quite a bit. And I want to work us through this and see if we can figure out what this code's doing. So let's start down in main. I have a vector of words. The quick brown fox jumped over the the quick red fox jumps over the slow red turtle. Okay? I don't know who wrote that, but that's not the standard way of saying that. I have this function called biggies, which takes in a reference to that vector, takes in the value 5, which is the size type for a vector. Okay? Size type for the string. Okay? And it also takes in default parameters for where to print and the spacing. Okay? So that's going to work fine. I'm now going to call this function stable sort and pass stable sort a Lambda function. Okay? To return a.size is less than b.size. First question, what do you think that stable sort's going to do? So on line 9 through 11, what do you think that stable sort with that lambda function is going to do? Yep, sort by length in increasing order. Okay, so the smallest length word should be at the front. Okay. On line 13 through 16, I have a variable I'm declaring called WC. Okay, word count, and it's using find if, and here's the lambda function. It's copying in SZ, which was defined up in the function pass in here, okay, so we have value 5 as being SZ, okay. We're passing in a string, or reference to a string, okay. And so return a.size greater than or equal to SZ. What do you think that lambda function on line 13 through 15 is doing? Okay, so the first thing we've done is we've sorted these things by length. What do you think this one's doing? Okay, let's go back to the definition of find if. We looked at find if on Thursday. Can someone remember what find if does? No, not quite. So find if goes over container and finds the first value that matches a set of criteria. And then it returns an iterator to that location. Okay? So the output from find if, you don't necessarily have to remember this, okay? This example is not in the exam, okay? I'm not going to ask you to tell me what find if returns, okay? But find if returns an iterator to the first location where something is true. And the something that's true is the comparator that you pass in. The comparator that we pass in this example is the lambda function. Okay? So we're finding the first place in this container that something's true. Okay? So what are we trying to find that's true? What is the lambda function in line 14 and 15 finding true?
The length of the word is greater than 5.
So it's finding the first place where a word is greater than 5. Okay? Yep.
Why do we use SZ in the capture list as opposed to just passing it as a parameter?
Why do we use SZ as a capture list instead of passing it as a parameter? Simply because this is the example. Okay? So if you look at, for example, the first one's got an empty capture list, the second one's passing by value, the third one's passing by reference. Okay? So it's simply for the case of the example, you could pass it in as a parameter.
Is there an advantage to doing it either way?
I don't know off the top of my head. Actually, no. Yes, I do know. Okay? I say I don't know, I do know. Go back a couple of slides. We said that SZ was passed in or copied in when it's created. At this stage, it doesn't matter. If we're passing it in as a parameter, it can be changed. Okay, so there is a difference between passing something as a caption and passing something in as a parameter. Okay. Okay, so this function, this on line 13 to 16, is going to find us an iterator to the first place where the word is greater than or equal to 5. Okay, so first step, we sorted. Okay, so we sorted our container, okay, from lowest to highest. Now we have the first location in that set of objects where the word is greater than or equal to 5. Now, I also want to find the number of words that are greater than or equal to 5. Because I've sorted the container, what's going on here? Let me clarify. Because we've sorted this container, we can get the iterator to the end and subtract that word count. Okay, sorry, I'm going to back up. I told you were wrong before. You're actually right. I got it wrong. Okay, find if is returning. No, it should be. We'll find if. Double check find if. This actually might be a bug in this code. Find if might be returning an iterator, might be returning a count. Okay, this next set of lines doesn't quite make sense. Okay, so let's double check the code. Regardless, we're finding the location in the set of values. Okay. Yep. It is returning an iterator. Okay. I still think there's a bug in this code. Okay. I'll have to double check it. I still think there's a bug in this code. What we're doing now is we're going into for each. Okay. And for each loop, we're starting with this iterator WC. Okay, so starting with this iterator WC. And for each element between this iterated point and the end, okay, here's another Lambda function. This Lambda function is passing in for output stream by reference, is passing in for character C by value, has a parameter of the string, okay, and is actually missing some bracing here. Okay, so there is bugs on the slide, so you're going to have to bear with me, okay? This hasn't printed out exactly how it should be. There should be squiggly braces around OS less than S, less than C, okay? Regardless of the missing syntax, what do you guys think this function is doing?
Printing out all of the words greater than 5.
Yes, so this is printing out all the words greater than 5 with a space in between them. Okay? So this one big function here has got 3 Lambda functions, is using the standard library algorithms to first of all sort the container, to find for first place whereabouts the word is greater than 5, and then print it out. Okay. Now that's all done in about 15 lines of code. If I asked you to write this code yourself, write me a function that prints out all the words in a container, whereabouts the length is greater than 5. This is probably not the way you would have done it. Okay? And probably your code would be longer than this. Probably. Okay? But hopefully you can see the ideas of how the Lambda functions can be very flexible and how this works. Okay, except for the errors on the slides, are we clear up until this point? What's going on? So here's the same version. This is using a function object. Okay? And so we still have the same Lambda function that we had at the start. Okay? So the first couple of lines are the same. Here we've created this function called check size, okay, which returns true if things are greater than or equal to that size that we've set there. Here we're combining this find if with bind. Okay, so this is bringing together what we saw at the start of today. Okay, and then we're doing the same thing. Okay, this version is correct with this for each over here, printing out that point there. Okay. So basically, the Lambda function version is the better way to go. Okay, but you can combine these things with bind and function objects and stuff like that. Anyone confused at this point? Okay, there is quite a few links to readings on the website. It might be recommended that you go take a look at. In particular, there's one, I can't remember what the site is now, it might be cppreference.com, that goes into a lot of details and a lot of examples about different ways you can use Lambda functions. Okay. So let's talk about captures. When we want to capture a value, when we want to bring something in from the local scope, we can decide to capture everything. Okay? It's probably not a good idea, but we can capture everything if we want to. And so, using just the ampersand like this, okay, everything gets captured by value. Okay? Using the equals, everything gets captured by reference. Sorry, I've got that from around. By equals, it's captured by values, with the exception of the things that go afterwards, they're captured by value. With the equals there, so with ampersand up there, everything's captured by reference, except for if you put stuff afterwards, it gets copied by value. I've got it right around this time? Yep. Okay, so you can, if you want to, copy everything in, or reference everything in. Generally don't do this. Okay? In fact, the Google style guide explicitly bans this. Okay? I'm not going to explicitly ban this. Okay? But generally don't do this. The whole reason why you write a function is so that you can limit your scope for errors occurring. Okay? So just implicitly capturing everything is probably not a very smart idea. Now let's talk about return types. What we're about to introduce is a concept called a trading return type. This trading return type is going to come back up when we talk about templates. Okay? So the lambdas that you've seen so far don't have return types on them. Basically, if the compiler automatically looks at your code and figures out what the return type of these functions should be. Most of the time, that's okay. Okay? So up on line 5 of this example, we have a lambda function which returns an int. Okay? So if I is less than 0, it returns minus I, or it returns I. Okay? So this is equivalent of the absolute value function. Okay? And so it automatically figures out at this return type needs to be an int. For this one, it's the same thing. Okay? So regardless of what syntax you use there, the absolute value, or its two absolute value lambda functions return an int. Okay? We can explicitly say it's going to return an int. Okay? By square bracing, taking parameter list, this arrow, and then int. Okay? The reason why you might do this is when it's not obvious what the return type should be. Okay? So sometimes you can end up in a situation where you've actually got multiple returns in your code. Maybe for multiple returns, need to do some typecasting or something like that. At that point, you need to put in a trading return type. Okay? So in a few minutes, I'm going to pause for a bit of a break. Okay? But the key things that you need to take from these slides and the slides from Thursday, okay, the key things that you need to take. You need to know how the operator overloading works in the sense of particularly overloading the less than operator, because it gets passed into these sort functions. Okay? You need to know the general idea of how bind works, and particularly those placeholders. So how bind wraps around a function, and how the placeholders can be used to substitute in values. Okay? For lambda functions, you basically need to know how to write a lambda function, and maybe how to write a lambda function that is equivalent to a less than operator, like you've just seen with that stable sort. Okay? You'll also need to know trading return types, but we'll bring those back up when we talk about templates, because I think they're more powerful, more evident when you see them used on templates. Okay? So that's the key take-home for those things. Okay? How to overload operators, particularly less than, how bind works, at least just at a very high level of how bind wraps around function objects. Okay? And with lambdas, you need to basically know how to write them, and you'll be writing them for assignment 3, you'll be writing them for assignment 4. You will be asked to write a lambda function in the exam. Okay? So at this point, I'm actually going to pause for about 5 minutes, 10 minutes, okay, because we're about to completely change track. What we're about to talk about is exception handling and some dynamic memory management stuff, but this basically, at this point, wraps up what we've talked about over the last 2 weeks in terms of classes and operator overloading and function objects and things like that. So has anyone got any questions at this point? No? Okay, what I'm going to do is I'm going to stop for 5 minutes. I've put up on the screen a bit of a question that you might want to work on over that time, okay, because this is going to come back up in the next thing we're talking about. I have 4 classes here, okay, and a main function, and the main function is creating an object B, okay. The only bit of this code that you wouldn't have seen before is this class B : public A. Okay, we're going to talk about object orientation in week 10 or week 11, quite a long way away from now, but just be aware that's inheritance, or the first time you've seen it. Okay, so class B is inheriting from class A. Okay, so over the next 5 minutes, have a break, try to solve what the output of this is while you take that break, okay? Cool. Okay, so I'm going to pick back up. So before we stopped, I left you with this question. Okay, it should be a very, very simple question. Okay, but this is just the type of this is the type of question you might get in an exam. In the exam, we have some multi-choice questions. This might be the type of question you might get. So, what do people think the output is? Who solved it? What's the output of this? Okay, what do people think? A? Why is it A? Who thinks it's A? Who thinks it's B? C? D? Who doesn't know? Oh, most of you don't know. Okay, it's a little bit scary. Okay, so let's work through it then. Okay, the short version is the answer is A. Okay, so well done for people who thought it was A. We have B. Okay, we are asked to create B. Okay, and we go on to B. Now, the constructor for B doesn't have a member initializer list. What does that mean? It means that these things get constructed automatically, okay, as well, okay? But also what we have at this point, okay, is this inheriting from A, okay? So if you haven't seen inheritance before, this might be why you're confused, okay? So class B, first of all, inherits from A, okay? So we go off and take a look at A. Again, A doesn't have a member initializer list either, okay? So it goes and default constructs X. X prints out X. Then, for body of the constructor in A runs, prints out A. Comes back to B. B doesn't member initialize Y, so it gets default initialized. So Y gets called up there. Okay? And then finally B gets called. Okay, so X, A, Y, B is the correct output for that question. Okay, so the guys who got A correct, here's question 2. Let's look at the destructors. What's the output of this? It's exactly the same question as before, it's just everything's been switched to destructors. What is the output? Reverse of A. Okay? So it's BYAX. Okay? So you should be able to answer questions that look like that. Okay? Now, admittedly, that had for inheritance, which you haven't seen before. Okay? But you should be able to look at problems like that and work them out. Okay, so what we're going to be looking at, what we're going to be looking at over the rest of today and then into Thursday and potentially next week is memory management and exception handling. And so the first thing we're going to look at is we figured we'll look at how to handle exceptions before we look at how to go and hurt yourself with dynamic memory. Okay? And so we're going to look at exception objects. We're going to look at try-catch blocks. We're going to look at catching exceptions, specifications, and handling them. Okay, and then we're going to look at smart pointers next week. Okay. Okay, but before we get into too much of that, let's talk about lifetimes. Okay, so a lifetime is the period of time in which memory is allocated for an object. And there are different types of objects. 3 different types of objects. There's static objects. Okay, those are objects that are allocated in the global or the static area. Okay. There's local or automatic or stack objects. Okay, we'd say we put things on the stack. And then there's heap objects. And heap objects, of course, are objects up on the heap. There's also named objects and unnamed objects. Named objects are the things that are named by the programmer. Okay? E.g., int I. I is an int, which is a named object. It's on the stack. Okay? And so the lifetime of named objects, e.g., int I, is determined by its scope. You create a named object by giving it a name and a type. Okay? And the lifetime of that is determined by its scope. Okay, you have no control over that lifetime. But with a heap object, their lifetimes are determined by a programmer. A heap object is where you go and create some stuff in dynamic memory, okay? And its lifetime can exist well outside of the scope in which, say, the pointer to it was created. Now, particularly if that object exists outside of the scope of which the pointer to it was created and you haven't passed a reference or a pointer down to that thing, you've got a memory leak, okay? Because you've lost the reference to that location in memory, okay? This is really important. Named objects are local stack objects. Their lifetimes are determined by their scope. Unnamed objects, dynamically created ones, have a lifetime that's allocated or determined by yourself. And so a local object might look like this. Int I equals 1. Okay? Its lifetime was created when f is called, and it ceased to exist when f completes, okay, with the destructors on the object being called. Okay, in the case of a primitive, like an int, there's actually no destructor for that, okay? Primitive objects are not initialized by default. You cannot guarantee that they are initialized by default. Okay? Class objects are initialized by constructors. Okay? And then memory management is done by the compiler. Okay? So local objects, the compiler handles all the memory management automatically for you. There's different ways in which we can look at local objects. Here's a stack of ints determined inside this scoping brace here. Here's a second stack of ints inside a second scope level. When we go out of that scope where that second stack was created, the destructor for stack S2 was called. But stack S1 still exists. When we go out of that second scoping brace layer, then the destructor for stack S1 is called. Okay? Local scope, easy. Okay? And so the destructors are called when the objects die. Here is a slightly different variant on the same thing. Here's a stack S1. Inside this second scoping brace, we create a reference to that first stack. When we go out of that scoping brace, does the destructor get called on that reference, and does stack 1 go and get destroyed? Hopefully this should be obvious, but when we go on to line 5 here, and this reference is about to get destroyed, does that actually go and destroy the stack object that's referencing? Hopefully the answer is clearly no. Hopefully. Okay, because the answer is no, because this is a reference that doesn't get destroyed. Okay? And we're not really going to talk about ownership at this point, but you could argue that the reason why it doesn't get destroyed is because the reference doesn't own the object. Okay? The ownership doesn't get changed at this point. Okay? Actually, we can talk about ownership. We're going to talk about ownership when we talk about memory management, okay? But this named object, S1, it owns the stack. The reference does not own the object, okay? And so the destructor in the second example is only called when S1 dies. Okay? This should be easy. Yep. Okay. This slide is a whole lot of text. It was a whole lot more text until I took a whole lot of text off this slide, okay? But this is important. Okay? We've just looked at local objects. Local objects are named objects that are determined by yourself, okay? But their lifetimes are determined by their scope. Temporary objects are different. Temporary objects are unnamed objects created on the stack by the compiler. Okay, there's a whole lot of rules for when they get created, but generally they're used during reference initialization, during the evaluation of expressions, including type conversions, argument passing, function returns, and evaluation of throw expressions. And so we saw that when we're looking at copy control. we saw about temporary objects could be created, particularly when you're doing copy assignment and things like that. Okay. These things get destroyed pretty quickly. Okay, temporary objects don't last for very long; they get destroyed pretty quickly. But there are some exceptions. Okay. When something is used as a temporary object for initializing the declaration defining an object, okay, so say an object copies something in, and we create a temporary object to do that, okay, the temporary object is destroyed when the initialization is complete. Okay, you wouldn't want it to be destroyed earlier, because if it was, your construction of the object wouldn't work properly. Okay. When a reference is bound to a temporary object, okay, we can create references to temporary objects. You would have seen that with R-value references. Okay. The temporary object is destroyed at the end of that reference lifetime. Compiler handles this stuff automatically again. Okay, but just be aware of temporary objects, what we can and cannot do with them. So let's take a look at this. Here is a function f that returns a standard vector created during the return type. The standard vector we create here is not named. We didn't give a name to the standard vector. Okay, so it's an unnamed temporary object. Okay? But see how we've got the reference here? This is an L value reference. Okay? So we want a reference to whatever that thing returns. Okay? This thing doesn't automatically get destroyed. It lives on as long as this reference is live. Okay? So, we've looked at local objects, we've looked at temporary objects. Let's go look at static objects. So there's 4 types of static objects. There's local statics, there's global objects, there's namespace objects, and there's class static objects. So memory management is done by the compiler. And these things are, of course, often referred to as global or static objects. And generally, we tell you do not have global variables. Okay? Global variables are static variables, where we'll see how they work in a few minutes. Okay? So here's a function. Inside this function, we declare int I to be static. Okay? We return from this function for pre-increment of I. This function, the first time we call it prints 1. The second time we call it prints 2. Because this static int I equals 0 only actually gets called once. Only gets called right at the very start when the program first executes. Okay? Oh, sorry, let me clarify. It only gets called when that function first gets called. Okay? So not when the program executes, so it gets called when that function first gets called. First time through that function, this int I gets 0. Okay? Because it's static, it goes into the static area of memory. Okay? And that memory is going to exist until the program completes, and its destructors are going to get called. Again, primitive objects are initialized to default values. Oh, I see them. Yep.
Is there a clearer way of doing this, like making the static in, that you don't? You know how you were calling, every time you call this, it looks like
Yep.
it's going to be reinitialized to 0.
Is there a clearer way of doing this? Write your code differently to not use statics. Statics are generally, for lack of a better term, considered evil. There is cases where you might want them. E.g., we saw that last week in the tutorial whereabouts we wanted to keep track of how many objects had been created. Okay? But generally you try to avoid statics for exactly these reasons. Your code looks like it's setting int I to be 0 every time around that loop. It's not. Okay? So in general, this is why these things are bad practice. Okay? So primitive static objects are initialized to default values. Class objects are initialized by constructors. And even though this thing is in memory all the time, okay, it's still only visible in that local scope. Let's look at for global namespace and class static objects. Here's file.cpp. It contains a global stack. Okay? Some people in assignment 1 created a global stack. We had a big debate with the tutors about whether we're going to punish you or not for that. Okay? Because generally we tell you do not use global variables. In the case of assignment 1, we actually let you get away with it with a big warning. Okay? But do not use global variables because they're not behaving in the same way in which normal variables behave. You can create a global or a namespace global static object within a namespace. Again, kind of not a good idea. You can also create a class static object. Okay, these are things that you might more often try to use. Okay, all three of these are created at program startup. Okay, so this is the mistake I made on the previous slide. Previous slide, this static gets made the first time if is called and exists until the program finishes. Global namespace and class static objects are created at program startup and exist the entire way through the execution of your program. Primitive objects are initialized to default values. Class objects are initialized by their constructors. Okay. So now we've gone through three. Local objects only exist while they're in scope. Temporary objects only exist while they're basically needed. Okay? So they have very, very short lifetimes. These globals, they exist for eternity. Okay? So let's take a look at heap objects. Okay? Heap objects are allocated via new and exist or persist until deleted via delete. Do not use malloc and free. Malloc and free is not C++. C++, we create things new and delete them with delete. So when we say int star pi equals new int 1, two objects are involved. Pi, which is the named object. Okay, I don't actually know why pi is equal to 1. Normally it would be 3.14. Okay, but here you go. I was pointing to an int. That's what it is. Okay, so we've got pointed to an int. It's a named object. It's going to persist while it is in scope. So a local scoped object. This new int 1 is the unnamed object, and it's on the heap. Pi is on the stack. New int is on the heap. Pi is named. Pi is local. New int is unnamed. Okay, there's no name associated with it. It's on the heap. Its lifetime is up to you. Okay? So Pi is destroyed at the end of its lifetime automatically. The pointed to object must be destroyed explicitly. If you do not destroy it yourself, you've got a memory leak. Okay? And so it's important to remember that when you say delete pi or delete dereference pi, okay, that's deleting for unnamed object. Delete pi and delete named, okay, doesn't make sense, okay? So delete pi is deleting for unnamed object, okay? So even though you say delete and you give it a named object, what it's really saying is delete for unnamed bit. Don't delete that bit until it comes out of scope, okay? And so the destructor for pointed to object, okay, is called, and then the memory is freed. Okay, so it's a two-step process, yep.
What happens if, because you mix malloc and delete, or new and free?
What happens if you mix malloc and delete and new and free? I haven't done that in a long time. All I can imagine is a lot of pain. You might get a segmentation fault. I'm pretty sure you probably would get a segmentation fault. They work in two completely different ways. Okay? Because remember when you're doing malloc, what you're doing with malloc is you're asking for the size of. Okay? So malloc basically isn't doing any type checking. It's just giving you a block of memory. Okay? Now this is, I've got to remember how C works, but I'm correct on this, right? You give it the size of and you ask for this particular size. Okay? With new and delete, you're still making sure you correctly call for constructors. You're making sure that for size of that object is all cleaned up automatically for you. Okay? If you mix them, I wouldn't want to know what happens. It's the short version. Okay, and remember the destructor for built-in type doesn't do anything. Okay? Okay, so I've got an example here. Okay? Inside main, I create a pointer to a thing that f is returning. F is returning a pointer. Inside f, I create a second pointer to a new int. This pointer is the thing that's returned. For new int isn't returned, for pointer is the thing that's returned. Okay, but remember, for pointer is the thing that's pointing to this heap object. So I can say pi is equal to new int, and now I can delete pj, and it works. Okay? Because the pointers are the local objects, and they're pointing to the same piece of memory. Okay? And for new int is the unnamed heap object. Again, this should be straightforward. Hopefully no one's confused at this point. If you are, let me know. Okay? So we need to make sure we call delete. Okay, that's the take-home message. We need to make sure for every new, we have a delete. Okay? Now, there's a couple of problems that can go wrong with deletes. Here we have pi is equal to new int 1. Okay, I have one int. I can also say new int, square brackets 10. Okay, and now I have an array of 10 ints, and those ints are uninitialized. And I can delete pi by saying delete pi. If I say delete square brackets pi, that's undefined, doesn't make sense, because the thing that pi is pointing to is not an array. Pi is just an int by itself. To delete pj, which is an int, I need to say delete square brackets here, pj, okay? And it deletes. Delete pj by itself doesn't make any sense because pj is an array, okay? And so an array object typically contains information regarding the number of elements it contains. Now, I wouldn't actually create a dynamic array of ints like this. I'd probably create a vector, and the vector contains int pointers. Probably how I would approach it. Okay? But you need to match your new and deletes with the correct types. Okay? And so here's a whole ton of ways to dynamically allocate and initialize objects. I can create a pointer, pi, which just says new int. Okay? It's an uninitialized int. Okay? I can say pj with call bracing like this, uniform initialization, and it's initialized to 0 by default. I can create a string by just saying new string, and it's initialized to empty because the default string constructor is called. I can create a second string by saying new string, uniform initialization, ABC, and so new string is initialized to ABC. I can say auto. Auto pointer. New, auto, whatever this thing is. Okay? And this is inferred to be float 3.14. I'm looking at this code a little bit concerned. You might want to double check this, this code. That actually might not be a float. Given what we looked at on Thursday, it's possible that's actually a list. We might want to double check that line 9. Okay? But we can infer stuff automatically. Okay? We can create a new const on the heap. We can create a new vector on the heap. Now, this is interesting. If this vector initialization fails, it throws an exception. Okay? We'll talk about exceptions soon. We have this version, new, brackets, no throw, standard vector. Vectors initialized to be empty. If the allocation fails, e.g. memory, returns a null pointer. So this top one up here returns some sort of exception. Here we've said don't throw the exception, and it just returns a null pointer. Okay? So there's lots and lots and lots of ways to dynamically allocate and initialize objects. But let's look at all the ways that now we can break your code. This gets fun. I have an int I. I have a pointer that's equal to that reference. I have a second pointer which is equal to null pointer. I have a double which is 3.14 and a pointer which equals that one. Okay. First of all, I try to say delete I. Well, I can't say delete I because I is not a pointer. I is a int object which is up on the stack. Okay. Next thing I say delete pi1. Okay, so pi1 was a pointer to a memory location for I. Well, I is on the stack, so it doesn't make sense to delete a stack object. Okay? And its behavior is undefined. So if top one will give you an error, the next one's undefined. It may or may not give you an error. If I say delete PD, yep, that's okay because I created PD with new. If after saying delete PD, I say delete PD2, okay, so PD2 is pointing to PD. Well, now I've got a big problem. This is called double free. What I've done is I've called delete on the same object twice. Okay? This, as far as I know, under GCC, and it's definitely happened to me, this will throw a segmentation fault or a terminate at runtime. Compile time, this is fine. At runtime, this isn't going to work. You've tried to free the same memory twice. Okay? So, do not free the same memory twice. Do not use delete on the same object twice. This is very, very hard to get around. Well, there is ways in which you can get around, but this is a very common problem in dynamic memory stuff, deleting the same piece of memory twice. Okay, it's called the double free problem. Now, we've deleted PD, okay? Let's assume that we've deleted PD, that's been okay. Let's assume that we haven't had our program stop working because we've tried to delete it a second time. Let's go to the next line. Dereference PD and set the value to 1. We've deleted PD. So we're now trying to access a dangling pointer. When we delete something, the pointer of where it's pointing to, that pointer is still going to keep pointing to that location we've now deleted, even though new data could be put into there. Okay? So accessing a dangling pointer is very, very, very dangerous. Okay? And it can cause memory corruption bugs. Now, PI2, which we defined up here as null pointer, we can say delete for null pointer. And that's fine. Yep.
When you go on start PD for 1.0, what if you were to create a new object there? Would that be okay?
So what was your...
It's a dangling pointer still, but if you say...
Oh yes, well that's not a dangling pointer at that point, because what you're doing is if you say, okay, so the question is this. On line 8, instead of saying star PD is equal to 1.0, what happens if I said new? Well, if I say star PD equals new 1.0, that doesn't make sense because it's the dereference at the start.
And you have something else.
Okay. If I said PD, okay, so lose the star, if I say PD is equal to new 1.0, that'd be fine because I'm changing the value of where that point is going to. The problem on line 8 is the dereference. I'm dereferencing something that's been deleted. Okay? Okay, so let's go back to line 9. PI2 is equal to null pointer. Deleting a null pointer does nothing. I can delete the null pointer multiple times. Does nothing. Okay? So the take-home message here is once you delete something, you should set the pointers to that location to be null. And then you avoid that double free problem. Well, it's one way of avoiding that double free problem, yes.
Is there a reason they haven't just chosen to set that pointer to null pointer after deleting it?
I don't know. I don't know.
It seems a little logical.
It seems logical, but at the same time, that setting that to null is still an operation. It takes time.
Okay.
And so there might be a reason why you don't want to do that. Again, writing very high performance, very fast moving code, you don't want to do So you don't want the compiler to do stuff that you're not expecting it to do. Okay? So you're playing with dynamic memory. Okay? It's up to you to fix your own problems. Okay? The compiler isn't going to do it for you. Okay, so I have a function foo which returns a pointer. The pointer creates a new standard vector of size 50. Yep, size 50. Actually, that might not work. That might have the same problem we had on Thursday. Okay, anyway, we're going to return pi. Okay, so int star pj is equal to foo. Okay, if the programmer never calls delete on pj, then you have memory leak. Okay, because the memory stored in the vector has leaked. Okay, lots and lots and lots of ways of having memory corruption bugs in C++. Okay, here you go. This is what I was just telling you. So, a deleted pointer is not automatically nullified. You should do it yourself. Okay, and we did the same thing when we looked at the move constructor last week. Because if we don't do that in the move constructor, okay, then when the object we move from goes and gets destroyed, hey, the new object you've created, well, that's now been corrupted. Okay. Now you may not need to do that in assignment 2. It depends on how you've written your code. You'll probably need to do that in assignment 3. Okay. So we need to make sure pointers get nullified after we've deleted from them. Okay, let's take a look at dynamic arrays. So we just had a big slide of all the different ways you can allocate normal types. Here's how we can allocate some dynamic arrays. Again, I'd probably prefer you didn't do this, that you did vectors, okay, but this is something important to know. Here's a pointer to an array of 5 uninitialized ints. Okay, so uninitialized. The next line initializes all of them to 0. Okay, so that call bracing is important. Here's a block of 5 empty strings. Because this is an object, not a primitive type, the constructor gets called automatically. So this next line is the same as the one above. Okay. If we try to say new int 5 brackets 1 like that, we get an error. Okay, because we don't have a constructor for int the same way we have for most objects. Okay. If we try to say ABC like that with that bracing, that old call bracing, we also get an error because it doesn't quite make much sense to it to do that. If I do some list initialization, new int 5, 0, 2, 3, 4, 5 like that, that's okay. And that's going to, in first position, put in 0, second position, put in 2, 3, 4, 5, and so on. Okay? In the case of the string array, if I put an inside here, the first string gets initialized with the value an. The other 4 are empty. Okay? So I'd prefer if you didn't do dynamic arrays, but be aware, even on construction of dynamic arrays, there's quite a bit that can go wrong, or do things you don't expect it to do.
Is there a way to initialize all the strings to AF, aside from writing it out 5 times?
Is there a way of doing that without writing out 5 times? Yeah, don't do it that way. That'd probably be the short version of it. Don't do it that way. Like, try to avoid dynamic arrays like that. Try to use more suitable containers such as a vector. Okay? If any of you guys have had me for for Java, second year 2.11 Java, I probably would have shown you how to do an array in Java once and then told you never use it again. It's kind of a similar idea here. Okay? Arrays are really primitive. There are reasons why you use arrays. Okay, the reason why you would use an array is they're fast. They're fast because they don't have all the overhead of all the object creation, moving about, all the call functionality and stuff like that. So they're fast, but they're basically just raw spaces in memory. And so that's one of the reasons why you can get all these sort of problems. Because you're just basically just getting a big block of memory and allocating it, and throwing some data in there. Okay? So there's fast ways of doing stuff, and there's slightly slower but more sensible ways of doing stuff. And I'd prefer you took the slightly slower and more sensible ways of doing stuff. Okay? But then there is also still very slow and very dumb ways of doing stuff. I prefer you guys didn't do that either. Okay? So let's talk about exceptions. We've just looked at all the different ways in which objects have lifetimes, all the different ways in which you can create objects, and all the problems that you can get with memory leaks. Look at exceptions. Exceptions are runtime anomalies. They're when problems go wrong at runtime, okay, and you know that something's gone wrong and you don't want your entire program to die. I'll say it right here. I hate assert. Assert is the most evil thing in C there is, or C++. Assert is evil because you figure it as an error, and instead of being nice about it, you're just like, oh, I'm not going to work anymore, just stop. Okay? Asserts are not very user-friendly. Okay? Now, asserts sometimes are needed if something critically goes wrong and you need to stop your program right now. Okay? So maybe if you're running a nuclear power station, maybe you'd want for assert to terminate something. Maybe also if you're running a nuclear power station, probably the last thing you want to have happen, because if you terminate, something might go critically wrong. And so exceptions are a way of being able to detect a problem and being able to say, hey, I've got a problem, can some other piece of code respond to this problem? Okay? And so it's a way in which there's communication between two unrelated parts of code. For example, a library function detects a runtime error and raises an exception. Okay, so a library function's gone, oops, I don't know how to handle this, you've given me invalid input. Okay? Hold on. If the user of that class library catches the exception, they should know how to handle it. Okay? So I haven't asked you to do exception handling in assignment 2 or assignment 1 for that matter, but say if I passed you, and please don't do this because it's an example, but say if I asked you in your Euclidean vector to divide by 0, okay? You could just assert and just go, I can't divide by 0, oops, I'm going to terminate. That's particularly dumb if you're writing class library. Your class library should not terminate somebody else's code. Can you think about how stupid that would be? If you write a class library, and that class library is going to go terminate somebody else's code because you call assert, I wouldn't use your library. Okay? If your class library goes, oops, I tried to divide by 0, here's an exception, okay? Then it's up to the user to catch that exception and go, okay, I've given it bad input. And either they can fix their code or the code can terminate. Okay? Simon.
Do try catch loops have associated performance?
Do try catch have associated performance issues? They do. And we're going to go into that, either today or Thursday, depending on time. Yep.
Does that mean for the non-script operator assignments, you should be using assert like the sample code does?
Does the sample code use assert?
Yes.
I have to double check that. Okay.
It asserts that the index is between 0 and...
Oh, sorry, you're talking about the sample code from the lecture side. So I probably didn't really use assert, I had assert. So should you be using assert in the... Checking if the index is valid. It's up to you. Okay, it's up to you. I'm not going to give you a test case that's got invalid data. Not for assignment 2. So for assignment 2, I'm not going to ask you, say you've got a Euclidean vector of dimension 3, I'm not going to ask you what the magnitude in dimension 10 is. It doesn't make sense. And we haven't covered exception handling until today. Okay, so no, I'm not going to check that. It's up to you whether you did still use assert or not. I'm not going to take marks off for using assert in assignment 2. Okay, if you use assert in assignment 3, I might do. Okay, so from this point onwards, don't use assert. Okay, are we clear about that? Yep. Okay. It's the same as the globals in assignment 1. We hadn't got up to a point of explicitly telling you not to use globals, even though you should already know that. So we didn't, unless you did something really dumb, we didn't take marks off. If you did do something really dumb, then we still did. Okay? I answered your question, didn't I? Yep. Cool. Okay, so let's talk about exception objects. Who knows how to throw exceptions in Java? About half of you. Okay. So in Java, you have to throw an object. And you generally throw an exception object. Okay? In C++, any object can be thrown as an exception object. I can throw number 100. I can throw a boolean. I can throw a character. I can throw a character pointer array saying it's a mess in here. It's not very descriptive. I can throw a double. I can throw a function call. And I can throw a standard exception saying, out of range, you are dead. Okay? Generally, you should throw a class object because you can communicate more information. The reason why you can communicate more information is the class object can contain state. Okay? So again, C++ lets you do many crazy and weird and wonderful things. Okay? You should be sensible about what you're doing. So you should be throwing a class object. And so, quite similar to Java, there's a whole hierarchy of exceptions that you can use. Your exception objects don't have to be extending or inheriting or using this. Okay, it's up to you. Okay, but be aware there is a hierarchy of exceptions. Generally, they break down into a logic error or a runtime error. Okay, and so a logic error might be something like being out of range. Okay, so in the case of assignment 2, if you get, you might want to throw an out of range exception. By the way, don't do this. Again, you don't need to for assignment 2, but if you wanted to, you could throw an out of range exception. That's a logic error. I've asked you to do something that doesn't logically make sense. Okay? A runtime error might be like an overflow error. Something's overflowed. That might not be a case of a problem in logic. That might be a case in terms of you've got a buffer that's either underflowing or overflowing. You've got something weird going on. That's a runtime exception. Okay? And so to throw an exception, here's an example. We've got a function called push, which is pushing something onto a stack. If the stack's already full, then throw this bad push. Okay, so this bad push is actually not a function call. This is a class, okay? So that should be updated to uniform initialization to be more clear about that. Okay? But here we go, we're going to throw bad push. Okay? Does anyone not know exceptions at this point? Like, does anyone have never seen exceptions before? Okay, so let's be very, very clear about this. When we say throw, at that point, the rest of the code below that does not execute. Okay? So when we say if fill throw, so if the stack's full and it's thrown, this line 3 doesn't get executed. Okay, just to be very, very clear about this. This exception class, okay, so I said before this is a function call. It's not. It's a call to the constructor to construct that function object. Okay? Again, this is why the updated uniform initialization makes more sense. Okay, so that should be updated to uniform initialization, like bad push. This bad push object goes and creates some information. What it does is it stores the index of where the push was. Okay. There's bugs in this code. This stores the index, or it should be storing the index of where it is. Okay? And it should be able to store some more information. It's not. This was just storing index, but there's class information you can pass through. Unfortunately, in that top up there, it looks like there's still some errors in that code because this const int reference here doesn't actually name a type either. Okay. And so once we're through an exception, we need to catch it. Okay. In order to catch the exception, we first have to try to do some stuff. So we've put some things inside a try-catch block. Try-catch blocks are another level to scoping. Try-catch blocks introduce a whole new scoping level. So I can create a stack, yes, okay? I can then try to push 3 things into it. I'm going to assume that the stack can only hold 2 objects. So when we get to this third one here, we get, for argument's sake, a bad push. And so we can cache this, bad push. And we're catching this in my reference. Okay? And we can say we've caught for bad push, here's the index that we were going into. Okay? If we have catch ... means catch everything. Okay, it's catch all. We can also catch built-in types, derived types, etc. And general classes are recommended. The type in an exception declaration cannot be an R value reference. Okay, because an exception is always treated as an L value. Okay, so we very rarely use R values or R value references. Okay, so you should always be catching something that can be used as an L value. So you should be catching it by reference, okay, but single ampersand, not double ampersand. Okay. So here's some examples. Okay. Try throw 100, catch a double, or catch an int. Okay. If this was function calls, this double, this 100 would go into a double. It doesn't in a try-catch block. There's limited type conversions. Non-const can be converted to const. Derived classes, so if we saw for class B inherits from class A earlier, okay, they can be derived to a base class. An array to a pointer can be converted to an array, okay, but there's not the standard sort of type conversion that you'd expect in the same way if you're calling functions. Okay. But because of this limited type conversion, if I say throw a logic error, and the first thing I say is catch exception, and the logic error inherits from the exception, it will get caught in this first one. Okay, because this is a derived class. Okay, so it's limited type conversions. In the case of these sort of primitives, it doesn't get automatically promoted in the same way. Then the second example for base class is where it gets caught. Okay. So in a hierarchy of exception classes, the derived classes should be listed earlier. Okay. You should catch exceptions by const references if possible. Okay. So C++ specifies that a thrown object is always copied, because it can't. Object has to be a local automatic object, basically. You shouldn't use catch by pointer, okay? Because then the question becomes who's responsible for deleting the pointer to object. Okay? There's problems with catch by value line. It's inefficient due to object copying. It causes the slicing problem, which I apparently mentioned in lecture 6. I don't remember mentioning the slicing problem, but we'll look at that if we need to. And it cannot exploit polymorphism and dynamic binding if we're catching by value. And so catching by reference avoids all these problems. Okay? So here we go. Here's a bit of a quiz. Might be a little bit hard to see, okay? But we have some code here to catch by value. Here, this is up on the right-hand side as well. Might be a little bit easier to see. And the question is, how many objects are created? This is the question. How many objects are created in this code? Let's start down inside main. Inside main, we say call function f. Function f comes in and says call function g. Function g comes in and says throw x. Okay, so at this point, we've created an object x. Okay, it gets thrown out of g. We catch by value. We catch by value on line 17. Okay. and therefore we've got a copy. We've got now 2 objects constructed. Now, we've called it, we're going to call throw a second time. So we're going to re-throw and catch it again. Gets caught down here. We've now created 3 objects. Okay, so this code, catching by value, has created 3 objects. Okay? So X was constructed, then copy constructed, and caught. One of the X's was destructed. A third X was copy constructed, then it was called in main, then 2 other ones were destructed. Okay, there's some links there for how the C++ compiler implements exception handling. Okay, because remember these things are kind of violating scope a little bit. We're moving some stuff around. Let's look at the same thing, but catch by reference. Okay, let's look at how many objects are created this time. Same piece of code. Try to construct F. Try to call F. F calls G. G throws X. 1 object constructed at this point. Catch by reference. Catching by reference. It's not constructed. 1 object still. Throw. Catch by reference. Same object. Only constructed 1 object. Okay? Yep.
Is that implicitly throwing X?
Line 11.
19.
Line 19. We're going to get to there.
Oh.
Okay? We're going to get to there. Hopefully. I'm going to wrap up in about 2 slides' time, so hopefully we'll get there. If not, we'll get there on Thursday. Okay? But that throw on line 19, and what it's saying is it's saying throw X again. Inside the catch, you can throw again. Okay? So we've got 1 object captured at this point. 1 object constructed, and it just gets thrown by reference. Ah, here you go. We did get to it today. There you go. So, this throw allows us to re-throw an exception. Okay, so from 1 catch block, we can do some stuff and throw it again. Okay? Now, if we catch by values, catch by value, when we call throw, the original object gets thrown again, not a modified one. If we catch by reference, we can modify an object, and when we throw it a second time, the modified version, because it's being thrown by reference, propagates down. Okay? So the reason why you might catch and then re-throw is, say you've got a whole hierarchy of issues going on. Okay? You try to divide by 0, you can't divide by 0. You catch that, and you pump some additional information into that exception class. But you can't handle all those details at this point, so you throw this further down. The next class down tries to handle it. Maybe it can't handle it. It pumps some more information into your exception handling class and throws it further down. Okay? So you can have a whole combination of catch blocks in different functions, and it comes down the stack. Okay? And so we're going to talk about stack unwinding. I'm actually going to stop here, but I'm going to pick this back up on Thursday, okay? But what I want to show you very briefly is this slide here. Say we have a stack like this. This is what we could talk about with stack unwinding, okay? The stack unwinding happens when we throw and it doesn't get caught. Each of the call stacks, each of whereabouts we've been, gets gradually destroyed until we get the exception caught somewhere. Using the rethrow, you can catch something in a particular stack frame, do something with it, and then throw it back out. That stack frame gets destroyed, and you keep on moving down there. Stack unwinding is quite a complicated topic, and it's got a whole lot of issues to do with memory management. So that's why I'm going to stop now. We're going to pick this back up on Thursday. Okay?